So the story of chapter 3 is space curves. Space curves occur in both of the applications we're keeping in mind this semester, topography and fluid flow. We'll use them in topography to understand traces of surfaces in 3 dimensions. For example, in the Tour de France, you often see maps like this. This is how the riders are going to go through the countryside on a particular day of the tour. This is, I think, Sunday's stage from 2020. And then you can see the trace of this path through the elevation function if you look at the stage profile. So looking at the stage profile, you're kind of seeing the height above sea level along the entire route, and this helps riders and fans understand where the difficult parts of the race are going to be. These really steep uphill sections are going to be really challenging, and things might happen there. As you've probably seen from my other videos, you know that I like to ride my bike. A couple weeks ago, I drove my bike down to Weston, south of here, and then got on it and rode up to a place called Tollgate in the Blue Mountains. And here you can see my route, and here you can see the trace of the elevation profile. So starting out just under 2,000 feet and topping out at about 5,000 feet. This is an application of a space curve, and the curve would be sort of the top edge of this profile. The other big application that we're keeping in mind this semester is fluid flow. Remember that in fluid flow, we use, we're going to use space curves to understand the motion of individual particles or molecules of water. So imagine the molecules of water flowing in this fountain. Each little molecule is following a trajectory through space, sort of a thread through space. And we can imagine that they're tracing out curves. This is happening in 3 dimensions. We can also talk about it in 2 dimensions. Just to switch gears a bit of a hobby of mine, aside from cycling that is creating little visualizations on the web. For example, the vector field flow example that we've been visiting from time to time this semester is something that I wrote, and it uses a pretty fun little programming library called P5JS. Here's the website for P5JS. And as usual with me, I'm using P5JS for 2 reasons. 1, it's free, and 2, you can put your programs on the web and therefore kind of share them easily. So accessibility. So free and accessible, that's kind of my mantra in general. P5JS was developed by a visual artist and programmer named Lauren McCarthy. She went to MIT and worked at the Media Lab there, and I think she's now maybe at UCLA or something. And forever grateful to her for developing this library. I've had a lot of fun with it over the years. For example, you can come into my studio here. This is just a big pile of P5JS programs that I've worked on over the years. I am really into writing visualizations where I set up an initial set of conditions and then I turn on the clock and I see what happens. This one is something that I call the Dandelion, and if you stare at it really closely, what you see are balls that just move in and out along the same radial path. And each ball is connected to its neighbor by a line segment that's either red, blue, or green. And furthermore, each ball is moving a little bit slower than its neighbor. So the fastest ball that's moving in and out is here, and then the next fastest is here, and so on, all the way around the circle until you get to this ball right here. This red ball at the other end is the slowest ball. And all of these balls moving in and out at slightly different speeds create really lovely interference patterns. Why am I showing you this? Well, I use a lot of the knowledge that I've gained through my understanding of Calculus 3 to write the trajectories of these little balls, parametric equations, space curves, etc., to give you these visualizations. Let me show you another one here. So I went to a conference years ago with my biology colleagues, and there was a person there talking about systems thinking. Systems thinking is the idea in biology that you can't just turn one knob and get behavior that you expect. You know, this depends on this, depends on this, depends on this, depends on this. And they introduced this idea to me of this equidistant group of people. So every person in the room picks two other people at random and tries to stay equidistant from them. And those people have picked two other people in the room and try to stay equidistant from them, and so on. And then they turn the clock on and everybody tries to move in the room to stay equidistant from their two particular partners. I thought that was a really interesting idea and decided to make a simulation in P5JS. And this is sort of a nicely organized collection of people, and everybody is staying kind of equidistant from everybody else. For example, this guy is equidistant from these two guys, this guy equidistant from these two, and so on. If I pull one of these guys out of place and then start the clock, this guy is going to try to stay equidistant from his partners, and his partners are going to try to stay equidistant from him, and so on and so forth. And they're all going to kind of get into this big, really complicated, complex dance. And you can see that they've settled into a new configuration. This one being equidistant from these two, you can see by the arrows, they end here with the arrowheads. So that means this dot is staying equidistant from these two dots. This dot is staying equidistant from these two. It's sometimes hard to tell, they get so jumbled up, but that's the idea. Now, these dots have found a really beautiful equilibrium, and if I move one of them, I'm going to mess it up. But they've adjusted. If I move another one, they're adjusting. And sometimes they have a really hard time adjusting. And they get off the screen and they do all kinds of crazy gyrations, and it gets pretty violent. And sometimes it even leaves the screen forever, like it's about to do there. Let me try again. All I'm doing is hitting the space bar to pause the simulation and then dragging dots around. And they're all struggling to be equidistant from their chosen partners. Sometimes it collapses like that. Sometimes it just keeps wiggling around forever. When they collapse like that, I usually pause it and pull one of them out and let it go again. It's almost like a living thing. And you can see the idea of systems thinking here. If I move one, everybody moves to adjust. And it's really hard to get this thing to do what you want. Now it's just in this little collapsed ball. If you want to try this yourself, you can just go visit my website and hit this URL. Let's try another one. You can see the little vectors in here, so you can definitely see that I'm using vectors like as in Calc 3. And these are all following their little trajectories as they move around. I've got a million of these things. I have a gravity simulation. Let me see if I can find that. So here's a little spaceship, and it is orbiting around some massive planet. And this is entirely simulated. It's using vectors of acceleration for gravity, and this little spaceship, the little triangle, is following its own little trajectory based on Newtonian mechanics. and you can see it's slowly drifting northward, and you might wonder why that is. And that's because when I start this simulation, if you notice, the ship started here, which means there was essentially a net momentum upward, and that drift is apparent in this simulation. If I were to add another ship over here going down, one going up, one going down, and started the simulation that way, it would stay stationary. I can add complicating factors like a little meteor that also kind of starts orbiting the sun, and now things are getting more complicated. And all of this relies on vectors and trajectories and space curves. And it seems pretty stable for now, but if you let it go long enough, it'll really start to kind of get crazy. And I can add more little meteors to interfere with things if I want. And I've had a lot of fun with this little simulation. And again, you can visit this URL and play with it yourself. Okay. Let's see, what else do I have? There's some really beautiful bird flocking simulations out there. So here's a collection of little red birds and blue birds, and they all just kind of start randomly, but they have this little bit of affinity when they get near another bird to want to travel in the same direction. But they also have this little bit of, they want to stay separate. So there's like this two competing forces. They want to stay together sometime. They want to stay near other birds and go in the same direction. They don't want to get too close to other birds because then their wings are going to hit each other and they're going to crash and so on. And this was an experiment that I had put together where the red birds have a little bit more affinity for each other, and the blue birds have a little bit more affinity for each other. And what you see if you let this go long enough is collection or flocks of red birds and flocks of blue birds. And you can tweak the separation and the alignment. If you turn down the alignment, they really kind of get scrambled, and if you turn down the separation, everything just kind of falls apart. And if I crank it up, I get better flocking. So they're so-called Boids. This is a demonstration by Craig Reynolds. And I just kind of copied his code and then tweaked it a little bit in P5.js. This lets you understand how a bunch of birds following their own little individual rules can turn into these large, beautiful flocks of birds without any group-wide communication or coordination at all. Flocking is what we call an emergent phenomenon. What else do I have? I think those are the big ones that really rely on vectors. And again, I just wanted to kind of share that with you. Each of these kind of requires introduction of objects like colored balls that move along space curves in 2 dimensions. And I just enjoy making these visualizations and playing around with them myself. And again, it's more about me setting up systems and then turning them loose to see what happens. That's one of my kind of favorite things to do. I've kind of rambled on here a bit, but yeah, Calc 3. If you learn a lot of Calc 3, then you begin to understand how these simulations can be designed